Okay, here's where we left off on Friday. Assuming we know how to put an OH group on a benzene ring, we need to be able to convert it to an ester. Assuming we know how to put an NH2 group on the ring, we need to convert that to an amide. And then, if we can put the OH group on the ring, I left you with how would you convert that phenol to an ester, or to an ether? So we all remember how to do the first two. Did anybody give any thought to how to convert the phenol to an ether? Nope. Because it can't go anywhere. Because remember, this is a double bond. So we've never written a vanillic carbon with a double bond with a positive charge. So it can't be, it can't be a traditional like SN1 reaction. Not from that side. No. Well, maybe. So you want to take the primary alcohol and you want to protonate that and then have this, like, do an SN2 reaction. And then lose H+. Yeah, you could do that. I mean, it'd be better. What would be even better is if you did a tertiary or a secondary or tertiary, because then you form a carbocation on this side, not on the phenol side. So yeah, you could do that. But I mean, the thing is, I want to synthesize an ether. So I want to know an ether synthesis reaction. It's someone's ether synthesis. Great. What's the Williamson ether synthesis, since I forget? An N minus, a C minus, H minus, or a potassium, or sodium or potassium, Well, I'm going to add some things. Alkoxide or hydroxide will also deprotonate a phenol, because phenol, if you remember, this goes back quite a while, that when you make a phenoxide, it's stable because of all the resonance structures you can draw. So phenol is a stronger acid and can be deprotonated by hydroxide or an alkoxide. Okay, so yes, we can do that, and that will allow us to make the a phenoxide. And then what do I add to the phenoxide? How about an alkyl halide? What kind? A primary or secondary? So then it undergoes what kind of mechanism? SN2, so then I just would end up adding my R group on the other side. What happens if I try and use a tertiary alkyl halide in this reaction? I'm going to get E2. So you could use any one of those reactions, but Williamson ether synthesis is what I had in mind. Okay, so that's, if I can get the OH group on the ring, that's what I need to do to make an ester or an ether, and I need to go from there. Okay, what other reactions with phenols do we have? We have one more. And that is, I'm going to take my phenol and I'm going to treat it with carbon dioxide and sodium hydroxide. So the sodium hydroxide is going to deprotonate the phenol to make a phenoxide, and then that phenoxide is going to kind of do a Grignard reaction on the CO2. So what will happen is, if I bring this pair of electrons down, let me rearrange my double bonds to this side. So if I bring that pair of electrons down and form a Cl double bond O, this pair of electrons can be used to attack the carbon, and then one of those pairs of electrons goes to the nitrogen. So that form that carbon-carbon bond. The issue is, I've now destroyed the aromaticity of the ring, so I need to reform the aromaticity. So I'm going to lose the H plus and then reform the phenoxide. It'll add either ortho or para, but most likely it'll add ortho. Because the negative charge is only going to move once, so it has to move next to where the O minus was to begin with. So I reform the aromatic ring, and then the H plus, then a couple of H pluses will come in, and I will make salicylic acid. And salicylic acid is the precursor to probably the most used drug in the world. And that is that we convert the OH group into an ester. And that's acetosalicylic acid. So what's acetosalicylic acid? Aspirin. I think it is probably the most taken pain reliever. So this is kind of an industrial preparation of salicylic acid. Salicylic acid kind of destroys the lining of your stomach, so it's not recommended. Salicylic acid is in birch tree bark. So if you're like stranded somewhere and you have a headache, you can find a birch tree and eat its bark, and it'll help solve your headache. You just can't take it every day or it'll destroy your stomach. So that's where acetosalicylic acid came into play. And that was synthesized by a chemist called Felix Hoffmann for the Bayer company. And then somewhere along the line, the E got dropped for him. Bayer is in Bayer aspirin. So that's an industrial strength preparation of adding a CO2, adding a carboxylic acid group ortho to the phenol. Okay. The last set of reactions that we want to talk about with aromatics is nucleophilic aromatic substitution. So nucleophilic aromatic substitution is going to be exactly the opposite of electrophilic aromatic substitution. So when I talk about a system being activated, it actually has what we have learned as deactivating groups attached to it, because I'm adding a nucleophile as the substituent, or I'm substituting a nucleophile, not an electrophile. So here, for instance, is an example of nucleophilic substitution, and there's going to be two mechanisms for this. I'm going to substitute that chlorine. I could substitute it for an NH2, except normally I would write this as NH2 minus, would be what I would react, but if I have NH3 there, it's the same thing. I'm going to go ahead and substitute that chlorine and add an NH2 group to it. So for nucleophilic substitution, having nitro groups or having electron withdrawing groups at the ortho and para positions activates the ring. So this is an activated ring because it's got electron withdrawing groups at the ortho and para position. So this is one reaction. I could also, for instance, take this molecule and react it with at least 2 sodium hydroxides and end up substituting the Cl for an OH. And so the mechanism that we're going to talk about is how these activated groups add, or do substitution, add and then do substitution. Okay. So an activated group, you need to have electron withdrawing groups. At the ortho and the para positions. And so that's what activates a ring. Exactly opposite of electrophilic, where the NO2 would deactivate the ring. Okay, so that's what we need to look at in terms of that mechanism. And so we're going to do this with 2 nitro groups at the ortho and the para positions. So our mechanism is going to look something like this. I'm going to write out the structure of the nitro group. Write out their explicit structure, and that's one of 2 resonance structures for that. So what happens is the hydroxide comes in and adds to the carbon that the chlorine is attached to. And then this pair of electrons moves to that carbon. So what I end up with is I end up with the OH and the Cl attached to the same carbon, and then a negative charge next to the nitro group. Now, what does the nitro group do for that negative charge? It helps to what's it doing in this structure right here? It's helping to stabilize the negative charge. And how is it helping to stabilize the negative charge? It's going to withdraw that negative charge, or it's going to take some of that negative charge by how? Induction and resonance. I heard some resonance. Anybody want to go for induction? Let's see what?
Well, for the ring to reestablish aromaticity.
You're down the road here. We want to stay where we're at.
Well, then the negative charge would follow. Sorry, the double bonds would break between the nitrogen and the oxygen, moving the charge up to the oxygen, and then the negative charge would form a double bond with carbon and nitrogen and oxygen.
That's resonance. Could it be induction, though? It's a positive charge next to a negative charge. So probably doing both. But which one's the more powerful of the two? Resonance. So there are a grand total of 4 resonance structures that you can draw for this intermediate. There's 2. There's 2 of the resonance structures, because you can have the negative charge next to the nitro group, or you can have the negative charge then move into the nitro group with another resonance structure. But what else could I do with that negative charge? What the other thing I could do with that negative charge is maybe I could take it and move it here and then move that pair of electrons to that carbon. And if I did that, I would have a third resonance structure that would look like this. And then what could happen here? Same thing. Same thing. So there's a fourth resonance structure you could draw. So the reason that the electron withdrawing groups have to go in the ortho and para positions is that I need to stabilize that negative charge once the nucleophile comes in and adds to the benzene ring. And if I don't stabilize it, there's no reason for a negative charged nucleophile to attack a benzene ring that itself is electron rich. Although it's kind of less electron rich when it's got 3 deactivating groups on it. So the 4 resonance structures that you get there are absolutely necessary in order to stabilize that anion. I'm going to rewrite the anion on the next page. You may not have to. So, going back to the original resonance structure, now what's going to happen is this pair of electrons is going to move to reform the aromatic ring system. Who's leaving, hydroxide or chloride? Which one's a better leaving group? Chloride is. And so now I've substituted the hydroxide for the chlorine, and so nucleophilic aromatic substitution. So this reaction can happen with an activated ring. And usually that activation is through 2 nitro groups, at least 2 nitro groups that are attached to a benzene ring. And nitros are the best because they're the most electron withdrawing, which means they're able to stabilize the negative charge the most. So you can substitute for that halogen or other leaving group by doing this kind of reaction. That's activated ring. How about a deactivated ring? Well, if I'm going to do a deactivated ring, I'm going to, first of all, I'm going to put the methyl group on there because I'm going to get multiple products of this reaction. Now, because this is not an activated ring, if I wanted to do this reaction, I would need to use something like sodium hydroxide and maybe like 350 degrees. I need to apply a lot more energy because this is not an activated ring. Okay, so if I do this, I'm going to substitute the chloride with an OH. But what people found was when they did this reaction, they actually ended up with two products. They ended up with the OH substituting at the para position. They also found the OH substituting at the meta position, and basically they were 50% each. So what that basically says is that the mechanism isn't the same. So the mechanism for an activated ring is different than for a deactivated ring. So what mechanism did they accept? And before I go on to that, you could also do this reaction using NH2 minus in something like liquid ammonia. In that case, you're not going to heat the ring up to 350 degrees. But if you did that, you would end up with an NH2 as your nucleophile, and you would still end up with a 50-50 mixture, para and meta. Okay, so what's the mechanism of this reaction? So for a deactivated ring, what's going to happen is either the hydroxide or the NH2 minus is going to deprotonate the hydrogen next to the chlorine. In other words, the hydrogen that's ortho to the chlorine. And then what's going to happen is that this pair of electrons is going to move here, and the chlorine is going to get kicked off. So it's kind of like it's doing an E2. And you could say, but wait, hydroxide's never removed a CH hydrogen in the past. Well, we're at 350 degrees. So we're at elevated temperatures. And then I'm going to end up with this species. And this is the infamous benzyne. Now, the person that proposed the benzyne had some explaining to do, because benzyne doesn't look like it should be very stable. Why not? What issue does it have? They're supposed to be linear. Are they linear in this case? No. So normally we would have a triple bond that's linear, but in this case, it's not. So that's the issue that it has. So it would be really difficult to observe this. I think people accept that this is the mechanism. The reason they accept it is because the experiment showed that you get 50-50 para-meta addition. Well, in this case, my second equivalent of hydroxide could come in and add to the left carbon to then put the negative charge on the right-hand carbon. Or it could attack the right-hand carbon and have the triple bond move to the left. So that we could end up with either of those two additions, either one of those two carbanions. And is there anything that's preferentially favorable to adding the hydroxide to the left or the right? Not really. So that's why you would expect, if this was the case, to get a 50-50 mixture. So then there's still water around, and so what happens is the carbanion would deprotonate the water to make the final two products. Para and meta. So this is the accepted mechanism for a non-activated ring for nucleophilic substitution. Right, so that's nucleophilic aromatic substitution. It's not necessarily done a lot. It does show up on certain types of standardized exams because it's something people are expected to learn. It certainly will show up on Friday if you look at some of the older exams. It certainly is on the problem set for Wednesday now instead of today. And I did get an email over the weekend. I got an email Sunday, I think it was, that said, I don't think we can do all the problems on the worksheet. Then I kind of remembered I needed to finish this stuff up. But then talking to somebody this morning, they're like, yeah, we didn't know whether we should email you or not. What's the worst case scenario in emailing me and saying, hey, I don't think that we can do all of the problems that you assigned us, particularly considering my track record of I've done that more than once during the year. And the more than once is probably generous, because that means it's like a 2 or a 3 times. So if that stuff happens, all you have to do is email me. Because as soon as I did that, I emailed the person, oh yeah, it's due on Wednesday. And then I sent out 2 quick emails, hey, we're not finished yet, so now we are. And if you look at Fridays, well, the older exams, you'll see that sometimes I put this in as a mechanism. Okay, but the two mechanisms are different. If I was to ask the activated, I might say, write the mechanism of the activated and write all 4 resonance structures. Or I might say, write the mechanism for an unactivated ring, and that goes through the benzyne, so it would look exactly like this. Okay, but this nucleophilic substitution does show up. I don't know that anybody really does it on a tremendous basis. I think one of our seminar speakers was talking about traces of trinitrotoluene in soils. I don't know, maybe I was at a conference or something, but I remember somebody saying that where there was a lot of training for World War II and a lot of either bombs being detonated or dropped or a lot of basically TNT being made, that the residues in the soils are pretty high. And so one of the things that there was a lot of debate about after was, could you use some sort of nucleophilic substitution to replace this methyl group? to then make that molecule something that's less explosive or less. I don't even think it was a question of being less explosive. I think it was getting in the drinking water. And I don't know what dynamite dynamite flavored drinking water tastes like. But it was getting into the streams, and it was getting into the aquifers, and it was getting into the drinking water. So they said, well, the only thing we can think of is trying to do some sort of nucleophilic aromatic substitution on that. And then there was a big debate as to how that would happen. So, not a generally really used reaction, but something that people are fascinated with. When people that write tests are fascinated with, including me. So that's pretty straightforward mechanisms. All right, so that should let you finish off your problems for Wednesday. I don't know if you had any questions about the problems for Wednesday, but that'll let you finish those ones off. So one of the things, if you've looked at some of the older exams, this test is going to be on, well, it's going to be on aromaticity, right? So this time, can you tell me if something's aromatic, non-aromatic, anti-aromatic, along with the adding different groups to the ring, along with orthoparameta substituents, along with side chain reactions, right? Both me giving you the kinds of problems you turned in on Friday, which I released the answer key for, and the problems on Wednesday, which for some reason the answer key showed up for at least a day on that. So if you were on top of things, you might have seen it there and could have certainly printed it out ahead of time. But somehow there were like 2 answer keys on there that I had to get rid of. So this is Canvas. So you'll also see that I may ask, I probably will ask, where I might say, okay, show me how you would make this molecule from benzene. Show me the series of reactions that you would use. So this is why you have to know your reagents, what reagents give you what group, and vice versa. So when you're thinking about a problem like this, there's 2 elements to getting it correct, right? First, I got to get a series of reactions that adds the 2 groups, and then I've got to get them in the right positions. So do we know how to add an OH group to the ring? How many steps? Just one?
No,
It's like 3 or 4.
yeah.
I think I've said them, including this morning. I think I probably haven't topped out at 10 yet, but I know that if you're going through this in your mind, let's see, OH group, you should be thinking what? NO2 reduced to NH2, diazonium, H3O+. You need to kind of know it that way. NH2, nitro, reduced down to NH2. Methyl group, Friedel-Crafts alkylation. So you need to know what two groups you're adding, and then you need to look at the substitution pattern so that if I'm looking at this OH, I know I need to put a nitro group on, convert that to an NH2 group, convert that to a diazonium, convert it to OH. But since these two groups are meta, they're meta. So here I have to take into account what? Which one should it, well, which group should I add first or start adding first, and then when should I add the other group? So in this case, what would you want to do? Add nitro first, and then the methyl, and then finish out the nitro to add the OH. Because the nitro group will make the methyl group go ortho, and then, or sorry, go meta, and then you can complete the rest of the molecule. So that's what you have to take into account when you do these problems, is you got to know how to add groups to the ring. So I would know this. I'd know that pretty cold. And to be honest, you probably need to know everything pretty cold. No, I had a research student many years ago who was in the lab doing stuff, and one of the students came in from lecture, and then I had to do something, so she was talking. They were talking, and she was like, "You need to know this, Cole. You need to be driving in your car, and when you're at the stop sign, thinking about exactly what reactions, you're doing." At least she added the stop sign part. But you have to know these things. I mean, she was giving her advice. I'm like, good advice, kind of harsh, but good advice. If it came from me, I would be yelling at you, quote unquote, yelling at you. But for some of these reactions like that, like putting the OH group on, they go in sequence. There's going to be that group things together that makes sense to group things together. We want to know how to add a carboxylic acid group to the ring. Right, a couple of ways we could do that. We want to know how to add a straight chain alkyl group to the ring. Without it rearranging. So as you go through, or if you've already started to go through, which would be even better, if you've started to go through your notes and organizing your reactions either into cards or on pieces of paper or on the computer, whatever method you use, whatever works best for you, you want to start grouping some of these reactions together and remembering what reagents go with making those groups. Not only for these problems, and usually I think you'll see that I might give three, and you do two, your choice of two of the synthesis problems. That's usually something that people struggle with. The other thing that people struggle with is when I give reagent 1, reagent 2, reagent 3, and then maybe like reagent 4, and say, what's the final product? And when you're doing these kinds of problems, you can stack your reagents up like that. You don't necessarily have to write every single reaction. You could write them like one HNO or HNO3 H2SO4, 2 Fe10 heat, 3 NaNO2 HCl. H4H3O plus. You can do that. I'm okay with that. That saves time. So you wouldn't necessarily have to write all the intermediates. That's correct. But if you kind of miss a couple steps in between, then who knows what you'll end up with. That's the same thing here. If you miss one of these sort of in the middle, you may not make it to the final product. That's usually why there's usually no 4, there's just the 3. And I gave you some of those for the problems for Wednesday. And that answer key is online, so you can take a look at it. I'll get you those back on Wednesday. And when I do, I'm not going to explicitly grade them, because I don't have the time to go through and grade each one. I'll take a look at them, and then you'll get graded on, like, hopefully you tried everything. Okay, if you tried everything and got it wrong, I'll notice that. But then then that puts the burden back on you to make sure you go through those problems to make sure you understand what you missed. Number 1, what you missed, and number 2, why. So it's going to be a lot of reactions. In terms of mechanisms, I could ask you an electrophilic aromatic substitution reaction mechanism. I could now ask you a nucleophilic substitution mechanism. Right. So that's kind of where we're at with this. And then we'll start on carbonyls, which is our last big set of topics next week. And I'm already kind of like 3 days behind, I think, in my lecture thing, and this is why flipping the classroom is great, because then I can just say, do all this stuff, and then I don't have to worry about getting behind. But I'll be able to catch it up in the aldehydes, ketones, and carboxylic acids and derivatives. So I'm not concerned right at the moment. So if you have any questions, email me, come see me. And if you have any questions on the problem set for Wednesday, same thing. What?